Hello everyone. This is section 14.7, Normal Lines and Tangent Planes, part 2. Last time we left off with this example where we saw how to find the tangent plane and the tangent line, or I should say, the normal line. So that was a tangent plane, and you'll have to fix this, go back. I'm not going to fix the last video just for this, so just make sure you fix this one. So that's the normal line. And one thing I also neglected to mention, recall that besides parametric equation form for a line, we could also have the vector form, where we'll state that xyz as a line is the point as a vector 2, 2, 2, and then plus t times the parallel line, which is, since we're looking for the normal line, the coefficients a, b, c, so 1, 1, negative 1. Okay, so I just wanted to mention that that's an alternative form. Okay, so with the approach we used here, remember this is an explicit function because c is given explicitly in terms of xy. Best thing to do, just to be consistent, always use the implicit form. Change it to a function of x, y, and z, then proceed by finding the partials and the normal vector, and then from there the equation of the tangent plane and consequently the normal line. So here we'll first form the function f of x, y, z again, and that is easiest to just simply transpose the z squared, so x squared plus y squared minus z squared. And then let me find the partials, going off to the side again. F sub x, 2x, f sub y, 2y, f sub z, careful of the negative, negative 2z. So therefore the normal vector in general at any point x, y, z, so as a function, is 2x times I plus 2y times j, and then minus 2z times k. So now the normal vector for our point is the point 2, 2, radical 8. Just plug those values in, so 2 times x is 2i, plus 2 times y is 2 times j, and then minus 2 times z is square root of 8 times k. So then it's probably easiest to think about that in terms of a, well, let's simplify that first, of course. We get 4i plus 4j minus 2 square root of 8 times k. Now you could actually factor out a 2 if you wanted to. Actually, you could simplify the square root of 8, and then that would be 2 square roots of 2. So that would make this 4 square roots of 2. And then you could factor out a 4 to make it simpler. But I'm just going to leave it as it is and proceed now by finding the tangent plane. And you may want to just consider that this just makes it easier to think of, that the normal vector ABC excuse me, in the equation for the tangent plane is just the coefficients of the I, J, K, respectively, of this normal line. So 4, 4, and negative 2 square roots of 8. Okay, so if you want to write down the equation of the plane again, a times x minus x 0 plus b times y minus y sub 0, or y naught, plus c times z minus z naught is equal to 0. So now we just plug in. Remember the point was 2 square root of 8, and so 4 times the quantity x minus 2 plus 4 times the quantity y minus 2, and then plus, well, actually minus 2 square root of 8 times z minus z sub 0 was the square root of 8, and that's 0. So let's do some algebra and put this in standard form. 4x minus 8 plus 4y minus 8 minus, okay, that gives us 2 square root of 8 times z plus, okay, this would be plus because double negative. Square root of 8 times square root of 8 is 8 times 2 is 16. That's equal to 0. So it looks like we get 4x plus 4y minus 2 square root of 8 times z is equal to, this makes negative 16 plus 16 is 0, so nothing to transpose, that gives 0. And you could, as I said earlier, reduce that further if you like. Okay, so now for the normal line. So the normal line, again, the equations, x is x0 plus at, pause this, hold on 1 second. Okay, sorry about that. So the normal line equation, x equals x sub 0 plus at, y equals y sub 0 plus bt, and move this up, z equals z sub 0 plus ct. So then that becomes x equals, okay, remember the point back up here was 2 radical 8, so 2 plus a was 2, so 2, or excuse me, a was 4, so 2 plus 4t, so that's back up here, the ABC normal vector. Y was 2, y sub 0 was 2 as well, and b was 4, so 2 plus 4t also, and then z would be the point square root of 8, and then minus 2 square root of 8 is the value of c times t. And again, if you wanted to put this into vector form, for the line xyz is equal to the point as a vector 2 square root of 8, and then plus, you could put the t in front as we normally do of the normal vector for 4 and negative 2 square roots of 8. Okay, so pretty straightforward. And we'll see one final concept in this section. So this is to find the acute angle that the tangent plane makes with the xy plane. And we say to consider these two vectors. N1 is the gradient, which is, remember, this is the normal vector. To the plane. And the unit vector k. And the reason why this works is because, just consider, because we're looking for the angle that, let's say, a plane here, and I'm not saying this is the plane that is in the example we're going to go over, but any plane, if it makes an angle with the xy, here would be the acute angle, okay? Here would be the obtuse angle, the one greater than 90, but that's the acute angle. And this plane, let's say, has a normal vector, let me say, that would be N1. Well, if we're looking for the angle, this angle that it makes with the xy plane, we'd have to consider this to be N2. That is the unit vector k, because then that would give us these two normal vectors, or these vectors to find the angle between them, would give us that acute angle. So if you recall from section 12.6, this was actually our manipulated form for the dot product of N1 and N2, or we usually called it U and V. But then we're just going to replace N1 and N2 by what we stated here, and we come up with this formula. Note that note two things here. This is the absolute value in the numerator that guarantees that we get an acute angle, because if cosine is negative, it's going to be in the second quadrant, and if it's positive, it's the first quadrant. So by making it positive, we know we get the acute angle. And then notice that the magnitude of k, so these are the magnitudes, notice the magnitude of k is just 1 because that's a unit vector. So it wants us to do a couple things here: find the equation of the tangent plane at the given point, and then determine the acute angle. So extra practice for the equation of the tangent plane. Form the implicit function f of x, y, z, easiest to transpose the 18, so x squared plus y squared plus z squared minus 18. We'll find the three partials. F sub x is 2x, f sub y is 2y, and f sub z is 2z. So then our normal vector at any point, or you can consider this to be the gradient, I suppose, because the gradient is the normal vector. So we'll say the normal vector at any point x, y, z is the same as the gradient of the function f of x, y, z, and that once again is just the partials. Okay, in general, let me say f sub xi plus f sub yj plus f sub zk. So I want to go with the gradient form. That's going to be 2xi plus 2yj plus 2zk. So then the gradient, which is the normal vector at the point where we 1, 2, and 1, 2 times x is 1i, plus 2 times y is 2j, and then plus 2 times z is 1k. So the gradient, which again is the normal vector at 1, 2, 1 is equal to 2i plus 4j plus 2k. And convenient, your choice, you don't have to, but in vector form, ABC would be 2, 4, 2. Get rid of that equals. Okay, so there's our normal vector. And so we then have to find the tangent plane. Okay, so just extra practice like we did before. Let's call it A. You don't have to write down the formula. X minus x sub 0 plus b, y minus y sub 0 plus c times z minus c sub 0 equals 0. So again, you could just jump right in. So 2 times x minus, okay, we're going back to the point. It was 1, 2, and 1. So 1 plus b times y minus 2 plus c times z minus 1 is 0. And of course, I'm being silly, can't substitute in the values of b and c, of course. Value of b was 4. Value of c was 2. Okay, and then manipulate this. 2x minus 2 plus 4y minus 8. And then plus 2z minus 2 is 0. So we'd have 2x plus 4y plus 2z equals, see, that's negative 10 minus 2 is minus 12. Transposed would be positive 12. And then we could divide by a 2 if we like. And this would be acceptable, but x plus 2y plus z equals 6 is a little bit, even a little bit prettier. Okay, so then the acute angle. So the cosine of theta was equal to the magnitude of the gradient evaluated at that point. X sub 0, y sub 0, z sub 0, dotted with k. It's the absolute value, excuse me. And then all over just the magnitude of the gradient evaluated at that point. And that's the magnitude. So we have the gradient is the 2, 4, 2. Note that k is the unit vector, and as in vector notation that would be 0, 0, 1. So therefore the cosine of our angle is, that's why it's convenient to put it in the vector notation here. 2, 4, 2 dotted with 0, 0, 1. Absolute value of that, and that's all divided by the magnitude of the gradient, and the magnitude of the gradient is the square root of the sum of the squares. So the square root of, I don't know what's beeping here, 2 squared plus 4 squared plus 2 squared. Okay, so the cosine of the angle is, remember, dot product, I times I, so 0, j times j, 0, k times k, plus 2 over the square root of 4 plus 4, 16, and 16 is 32. Okay, so the cosine of theta is 2 over the square root of 32. So theta is the inverse cosine of 2 over the square root of 32. And obviously going to use a calculator for that. And let me see if I got one here. Pause this for one quick second. Okay, so going to a calculator, the inverse cosine of 2 over the square root of 32 is roughly 69.3 degrees. Okay, so that ends section 14.7, and when you're ready, come back and we should have 14.8 ready soon.